Narayan received his bachelor's degree in electrical engineering from Diyalbag Educational Institute in 2008. For a couple of years, he worked at Schlumberger Technical Services before joining the University of Waterloo, Ontario, Canada, where he is presently pursuing his doctoral studies at the System Design Engineering Department. At the University of Waterloo, he has been awarded the University of Waterloo Graduate Student Scholarship for Excellence in Academic Performance and is a member of the Review Committee of the Graduate Student Endowment Fund and also of the University's Student Technology Advisory Committee. In addition to having been given invited talks at UW, he has been a reviewer for IEEE Potentials and chaired a session at the 2009 IEEE International Conference on Systems, Man and Cybernetics. His area of research are artificial intelligence, neural networks, design optimization under uncertainty, and quantum computing. So today he's going to talk about design optimization and analysis under uncertainty.
I would like to give special thanks to the organizers for inviting me to this school. And I would also like to thank Professor Keith Heipel, who is here and who has been my mentor for the past 1 year at the University of Waterloo. This talk is from the perspective of a graduate student who is in the initial stages of its doctoral studies. So my talk will not delve deep into the ideas of quantum computing or nano computing, but I'll try to extract ideas from quantum computing to develop engineering systems in a more robust way, to optimize those systems in a more robust way. So as my title suggests, I'm going to talk on design optimization and analysis under uncertainty. I would refer to various kinds of uncertainties in the systems and approaches towards modeling those kinds of uncertainties and optimizing them. Here is an outline of my talk, and where I will start with talking about what kind of uncertainties we have while designing systems, and then moving on towards optimization under uncertainty, which will be a major part of my talk, and then a couple of traditional techniques which are already there for optimizing such systems. Then we'll talk about modeling systems with uncertainty, and this is of significant importance because all systems, all real-world systems have uncertainty inherent in them, and when we try to model those systems, we need to incorporate that uncertainty into the model itself, so we are able to precisely characterize our systems. And also it's very important when we are trying to simulate our systems for longer duration of time because of the rare availability of the data. So this is of quite importance. And then most of the second part of my talk, I'll focus on a special type of evolutionary algorithms, which are the quantum-inspired evolutionary algorithms, which I was introduced in when I was an undergraduate student at DEI, and then I extended that when I'm doing my PhD at Waterloo. And then we'll conclude the presentation and open the floor for any questions, if any. So uncertainty and design. So I guess a lot of people over here in the audience would be aware of the various concepts which I'll talk about in terms of what kind of uncertainties we have. So there are basically two major kinds of uncertainties, the probabilistic uncertainty and possibilistic uncertainty. When we have these uncertainties, we need to have some kind of a metric or measures to measure this uncertainty. These measures of uncertainties have been really very well studied by George Clare in his book on generalized information systems, in which he has talked about quite in detail the various measures of uncertainties in his latest book on the generalized information systems. Then I'll talk about optimizing systems under uncertainty, because once we have our system model available and we are trying to implement that in the real world, we need to optimize our system so that it is robust and is able to handle all kinds of uncertainties in the system. So as I mentioned previously, we'll talk about two major kinds of uncertainties, which are the probabilistic uncertainty and the possibilistic uncertainties. So in a probabilistic uncertainty, the uncertainty basically comes from three major sources. As we all are aware of in the real world scenario, in real world we have a lot of inputs or uncertainties. All inputs are uncertain in real world. So we need to have a system which can handle those kinds of uncertainties. In a model, suppose we have a model of the form of z is equal to f of xp, where x is a variable and p are the parameters, then we have uncertainties in parameters as well. And the most basic uncertainty would be uncertainty in the model structure itself, because when we are trying to model our systems from the real world, it may be possible that we are not able to model the system accurately. So we have uncertainty in our models as well. So when we are handling these kinds of uncertainties, we need to make sure that when we are trying to optimize, it considers everything in the domain. So we model uncertainty in a probabilistic sense when we are talking about probabilistic uncertainty. So given this function, z is equal to fx plus epsilon x. So epsilon x is basically uncertainty. It may be multiplicative, it may be additive, and then we need to have some kind of function representing that uncertainty. So we use probability density functions for representing that uncertainty. Now, which probability density function can represent our uncertainty accurately is a matter of judgment, a statistical fate, or it depends on various standards. So like I've been working on renewable energy, where wind energy can be it's a standard, and it's been found that the Rayleigh or the Weibull distribution fits it very well, and it's been used across the standard in the US. Moving on to the fuzzy uncertainty, it was introduced by Lofty-Zadeh and Dieter Crow in 1965 as an extension of the classical notion of the set. And fuzzy and probability are basically just two kinds of ways of representing uncertainty, and they have their own notions when explaining uncertainty. Fuzzy set theory uses the idea how much a variable is in a given fuzzy set. So for example, if we look at this figure, there are three fuzzy sets, 1, 2, and this black line is basically the numerical value of a variable. So it says that how much is the membership of this variable in all the three fuzzy sets. When we have this, so there's a separate system for identifying what our values of the system would be. So in a given fuzzy system model, since we obtain values from the real world in the numerical sense, and this fuzzy system understands fuzzy values, so we need to fuzzify our numerical inputs, and we have to have a fuzzy inferencing system. A fuzzy inferencing system basically has to understand the fuzzy input and move on and give some output which has to be defuzzified and given back as a numerical output to the real world system, which understands basically those values. But how does this fuzzy inference system works is basically we need to have some fuzzy rule base. It's basically coming from the expert knowledge which we have, or we can basically, now we have intelligent algorithms which we use to produce this fuzzy rule base and have this fuzzy inference system. I will not talk much about this now and move on to dynamic system modeling under uncertainty. Mostly all dynamic systems in the real world are subjected to uncertainty, as I mentioned, and they are an integral part. Unfortunately, when modeling these systems, we never consider these uncertainties. So just assuming a simplest dynamic system, we model using a differential equation dy by dt is equal to I minus O, where suppose any system is I is the input, O is the output, and Y is the state of the system. In the real world, if in the simplistic terms, it can be understood as a reservoir or a catchment. But the input and output to any of these systems is not deterministic. And what I mean by deterministic in the sense that input, suppose in case of a reservoir, it's a rainfall which is uncertain and we are not aware of. And output, which is basically the flow or the evaporation or seepage to the ground, is also uncertain, so we are not aware of as well. So we use the idea of stochastic differential equations to model these uncertainties. So in this equation, if you look at this term of neta 1 and neta 2, which are basically Wiener processes, which incorporate the uncertainty into the system. Now, and the problem with this model is all these integration schemes which we are aware of do not apply to these kinds of equations. So there's another branch of calculus known as stochastic calculus, which we use to solve these systems, because this integration cannot be represented in the Riemann-Stieltjes standard integration form. So there was another branch of calculus developed by a mathematician from Japan, whose name was Ito, who came up with the idea of Ito calculus, in which he gave a scheme of integrating these differential equations to get the state of the equation. And then there was, so since this was in the Japan, so there was another mathematician, Stratonovich, who came up with his own scheme of integration. Both these schemes are really well understood and in detail, but the point is, when we are modeling these large-scale systems, we need to have a scheme for numerical integration so that we can model these systems and run our simulations. So all the engineering systems, when we are trying to model engineering systems, they are very well understood in the Stratonovich form. But the problem is, Stratonovich form does not have very easily implementable numerical integration schemes. For numerical integration schemes, we have only for Ito calculus. So what people found out, they found out a transformation between Stratonovich and Ito. So when we understand an engineering system, we model it as Stratonovich, convert it into Ito, and then apply our numerical integration schemes and find out the state of the system. Now once we have already modeled our system, we need to perform optimization so that we have a robustness in the system. And optimizing the system with stochastic elements, either in its data, objective function, or its constraints. So when we have a model of a system, we have uncertainties and stochasticity in either the data, objective function, or the constraints. So we have various schemes for optimizing evolutionary algorithms, stochastic programming, simulated annealing, global random search. And I'm going to focus today on evolutionary algorithms and a specific type of evolutionary algorithm, which is the quantum-inspired evolutionary algorithm. So looking at this, when all these evolutionary algorithms are basically kind of population-based and global random search kind of algorithms in which we have a random sampling of points at which the function is evaluated. There is a randomness in the system, but it's an intelligent randomness where we cover the entire search space intelligently so that we avoid the problem of premature convergence in those algorithms. We do a frequent selection of new points near the previous good ones, and I'll talk about when I'm discussing the algorithm. And we need some inferencing of the results so to direct our algorithm to the positive or the best solutions. And as we proceed on with our solution, we kind of reduce our randomness so that we move on to the better and better solutions and don't waste times. So in the global optimization schemes, we have evolutionary algorithms, simulated annealing, genetic algorithms, neurogenetic, fuzzy genetic, and then this new class of quantum-inspired algorithms, which was introduced in the last decade in 2002 by Han and Kim. So to mention clearly that this is not a quantum algorithm. It is a classical algorithm, but it can run on, and it can run on only classical computers, but it takes ideas from quantum computing for higher representation and robust search so that we can avoid the problems faced by the generic evolutionary algorithms or the genetic algorithms. This was first proposed by Han and Kim in 2002, and so this is a stochastic search algorithm where we stochastically search the entire search space in an intelligent way using the quantum representation of our qubits or the entire string. So this is basically a pseudocode for the algorithm which was proposed by Han and Kim, and I'll not talk in detail about the intricacies of this algorithm, but will only focus on the ideas where quantum computing comes into the play. So we initialize the qubits, we observe the qubits, and after observation we generate a classical bit string. Then we perform generic operations of a normal evolutionary algorithm or a genetic algorithm, and at the end, once we evaluate the fitness of our string, we update a qubit string using a quantum rotation operator. I guess this representation will be very easy to understand for the audience who knows in much more detail the quantum computing, where alpha square and beta square are the probabilities of the qubit string being in the state of 0 or 1. And this is the representation of the quantum rotation gate, which we used for updating our qubit string. So I'm going to basically talk about three kinds of problems which I've been working on since I was introduced to this idea of quantum-inspired algorithms. I'll talk about the combinatorial optimization problems, and I'll give an example of the knapsack problem. Then I'll talk about numerical optimization problems where real valued function optimization we are trying to do. And the current research problem which I'm working on is the smart grid design in the area of renewable energy. We are trying to develop renewable energy systems, smart systems, and I'm trying to use these ideas from quantum-inspired algorithms to come up with smart systems. So this is basically a very simple formulation of a knapsack problem. Just to tell in a small, short time what is a knapsack problem, you are given a set of items which has a given price and weight, and you have a given knapsack which is a capacity, so you have to choose items in a way so that you have maximize your profit and do not violate the constraint of your knapsack. A more generalized problem of the knapsack problem is the quadratic knapsack problem, in which you have a correlation structure between the items you choose. So there is not just a single profit, it's not a one-dimensional problem, it's a two-dimensional problem, and it's already shown in the literature the knapsack problem is an NP-hard problem, and quadratic knapsack is a more harder problem to solve. And in the graph theoretic interpretation, this can be understood as one of the clique problems, the clique graph problem, and then we can go ahead and solve that. So QKP is basically a generalization of the knapsack problem. It can be shown that QKP is a generalization of the clique problem, it being one of the strongly NP-hard problems, and hence QKP is as well a hard problem to solve. There are solution schemes using the cutting plane and semi-definite programming techniques. There also have been EAs and GAs being employed to solve these problems, but they face the problem of premature convergence, and which we are trying to avoid using the ideas of quantum-inspired algorithms. And they find various application in engineering design problems, in network design, site location, and satellite positioning. So this is the generic algorithm for the quantum-inspired for the knapsack problem, and I'm not going to talk about the entire algorithm because it's very similar to the one proposed by Han and Kim. But when we are talking about any specific problem, we need to implement some operators which exploit the structure of that problem. So we implemented few operators to exploit the structure of the knapsack problem, and a couple of neighborhood operators which exploit the search space. So in the beginning of our search, we kind of explore the entire search space, and when we are reaching the end of our solution, we try to exploit the small regions of the search space so that we find better and better solutions. And these are a couple of our experiments which we performed with the variations of the neighborhood search operators to find out which was the best. And it found that initially you have to use the exploration operator much in a larger, if more frequently than the exploitation operator. Now we'll move on to the numerical optimization scheme, where we need a real number encoding instead of binary numbers, and a continuous representation is required. So this will give you a different flavor of how quantum-inspired algorithms are used, and we use the idea of probability density function of the qubit strings. So we generate the genes of the qubit strings and find out the probability density function of our qubit individuals, and then which enables us to generate our classical bits from that, and we can then perform a couple of operations on them, which I'll just talk about. So this is basically pseudocode of the algorithm for the numerical optimization scheme, but I'll just focus on a couple of important points in this pseudocode, where we initialize the quantum population QT with n individuals with each gene. So each quantum individual is made up of G genes. Then we create the probability density function of our quantum individuals, and once we have the probability density function, we can generate the cumulative density function and generate the classical population, and we evaluate the entire classical population using the ideas of genetic or evolutionary algorithms. And once we have our solution, we go ahead and update our qubit string. So in this, again, we apply the quantum rotation operator, but in a different sense. So initialization of the quantum population is the Q is made up of n quantum individuals. Each quantum individual is formed by G genes, each of which has two values, which is the mean and the width. So if you look at this, this is a sample quantum gene which has got a width and a mean. And the height is made sure that it lies between 0 and 1, because when we are trying to find the probability density function, so it always remains in the range of 0 and 1. Now observing a individual is we sum up the individual quantum individual from all the genes from which it is being formed, and this gives us the probability density function. And observation made using these individual probability density function will result in classical individuals, because once we have the PDF, we can find out the CDF. Now, updation of qubit string in this case is a two-stage process, because our quantum gene is represented by two parameters, which is the mean and the width of our string. So we first replace the mean of each gene with the value of our classical gene, and now we shrink or expand our quantum gene by using the quantum operator. When we are trying to shrink or expand our quantum gene, with basically what is happening is each quantum gene is representing various intervals in the entire search space. So we need to make sure that we do not void our constraint of the search space and remain in our domain. So these are a couple of functions on which we implemented this algorithm, and these are the domains. And right now what I'm working on is smart grid micro design, and which is basically not exactly into quantum computing as such, but it's a very complex problem because we are talking about distributed generation with more penetration of renewable sources of energy. Now, when we talk about renewable sources of energy, it has inherently so many uncertainties because of the meteorological parameters, and we need to make sure our system models them accurately and precisely. This idea of smart grids basically talks about it has an intelligent energy management system, it is self-healing, and we need to talk about an optimal capacity design where we choose appropriate wind, solar, hydro, and biomass, and any other renewable sources of energy. When talking about PV and wind, we already know that they have a lot of uncertainty. A small cloud cover may cause a lot of uncertainty to the system, and wind is really unreliable. I've been working on it, and I've found that it's really difficult to get accurate measures speed and hence ensure how much. So when you're modeling this capacity, we need to make sure that our design is highly robust. And this gives us a very complex mixed integer nonlinear programming formulation, and which we are trying to solve, and we are still working on this. And our search space is highly large, so we need to make sure that we use these algorithms to optimize our search space so that we get solutions pretty fast, which are more robust. And this is basically my current area. This is the optimal capacity design, which I'm looking forward right now in the beginning of my doctoral studies, and maybe at a later stage I'll look at intelligent energy systems and self-healing. So here's the conclusion of all what I talked about. I talked about handling uncertainty in the systems given a probabilistic and a possibilistic approaches, optimization schemes under uncertainty where we have stochastic programming, simulated annealing, stochastic search algorithms as evolutionary algorithms, genetic algorithms, QEAs, etc. In QEAs, I basically talked about the knapsack problem, the numerical optimization schemes, and the future application and designing of smart grid systems for future energy systems. Thank you for your attention.